All right, so this is 3.4, zeros of polynomial functions. There's a lot to discuss in this section. Let's just get right to it. So first we see the fundamental theorem of algebra, which is often abbreviated FTA for short. And it says that a polynomial function has the number of zeros, its number of zeros equal to its degree. And this, of course, includes repeats and non-real numbers. We'll do an example of this shortly, but just keep that in mind. The degree of a polynomial tells you exactly how many zeros it has, but you have to keep in mind the fine print here. It includes repeats and non-real numbers. Okay. Linear factorization theorem says that any polynomial function with degree n bigger than 0 can be written as the following. F of x equals a times x minus c1, x minus c2, all the way to x minus cn, where c1 through cn are the complex zeros of f of x. Now, there's kind of some subtlety here. I say complex. Remember, a complex number is a number that is of the form a plus bi. Okay? But now, it is possible that this is 0. So maybe 0. And what if it is 0? Well, if it is 0, then it's just a real number that's our 0. So when I say complex, it's kind of a vague term. It means it can be anything. It could be non-real or real. That's what I mean by complex. What else? Oh, a, if you expand this out, you'll get your, well, if you try to, not expand it out, but if you try to FOIL it out, you'll get how many hits of x. Well, since this is counted C1, C2, C3, all the way to Cn, there's n factors, meaning there's n x's. So if you FOIL this out, actually, you'll get x to the n will be the degree. And then distributing a, you'll get ax to the n, meaning this a is our leading coefficient. So I'll abbreviate leading coefficient as a LC from here on. And now we'll take a look at a few examples. So here we're asked to find zeros of the function and factor it into its linear factors. So with the first one, so they're both pretty different actually. But for the first one, to factor this, remember we want to set it equal to 0 to find its zeros. And to factor, we're going to notice that it is a difference of squares. Technically, you can write this as x squared squared minus 1 squared. 1 squared, of course, is just 1. Now that we've written it as a difference of squares, we can actually factor it as, well, let me, yeah, it's fine. So it's x squared minus 1 times x squared plus 1. And you can see, if you FOIL this out, you'll get a cancellation of the two middle terms, and you indeed get x to the 4th minus 1. We can go further and apply the same argument. If we factor this, then we get x minus 1 times x plus 1. Similarly, since we're setting it equal to 0, you can set x squared minus 1 equal to 0, add 1 to the other side and square root. When you square root 1, you get plus or minus 1. So that's what we'll get from this anyways. When this is 0, though, well, something funny happens. So there's actually something we could do. You could try to treat this as a difference of squares, but you'd have to treat it as x squared minus negative 1. And with that being said, well, you have to ask yourself, negative 1 is what number squared? X squared minus what squared? Well, I squared is negative 1, so this is going to be x squared minus I squared, meaning it actually indeed does factor as x plus I times x minus I. Okay, another way of seeing this is if we had set x squared plus 1 equal to 0, much like what I said for x squared minus 1, you would subtract 1 to the other side to get x squared is equal to negative 1, and then square root to get plus or minus the square root of negative 1, which is of course plus or minus I. So there's two cases here, it's I and negative I, and from what we saw from the linearization theorem, or the linearization factor theorem, linear factorization theorem, we can write a factor as x minus each of these zeros. So one of the factors will be x minus I, the other one will be x minus negative I, but notice double negatives make it x plus I. So there we go. So let me just erase this and kind of actually write an answer here. So through difference of squares, I was able to completely factor into its linear factors. Linear, by the way, means that the degree of each factor is 1, so there's no power on x, and that's exactly what we have here. Notice, since the degree is 4, there are 4 of them. They may be the same. Some of them may be the same. In this case, none of them are the same. but they may be the same. In this case, they're not. Also, some of the zeros may be non-real, like I is non-real, so there's an instance of that. Also, the zeros, what are the zeros? Well, as you may notice from the zero factor theorem, it's just a sign change of what's next to x. So the zeros are actually, in short, plus or minus 1 and plus or minus I. So I've done two things here. Factored, and then I found the zeros. You realize kind of doing either one in either order is kind of the same, because zeros and factors kind of have this one-to-one correspondence. And that's basically why I introduced the fundamental theorem of algebra that had to do with zeros, and the linear factorization theorem that had to do with factors, and it kind of relates to each other, basically. Here, notice they all have x in common, so we'll pull x out. And now we're left with this, which actually factors. This factors as x minus 2 times x minus 2, or if you like, x minus 2 squared. Meaning 2 would have a 0 of multiplicity, well 2 would be a 0 of multiplicity 2 because it appears as a factor twice. X minus 2 appears as a factor twice, if you recall from 3.3. So this is actually it. This is our factorization into linear factors. Notice since x minus 2 is a repeat, you get x minus 2 squared. So if you want, you can write this as x times x minus 2 times x minus 2, but I'm writing it like this, the power. The zeros then are what? The zeros are, well, when x is 0 for the first factor, you just get 0. When x minus 2 is 0, you get 2. But I'm going to point at 2 and say this is multiplicity 2. So the fundamental theorem of algebra, again, includes multiplicity. And notice, just like here, there were 4 zeros, right? 2 pluses and 2 minuses. The degree was 4. Here, there are 2 zeros, but again, since 1 is multiplicity 2, if you include repeats, there are actually 3 zeros, and the degree is 3. There it is. The degree is 3. Okay, moving on. Okay, so now this is the rational zeros test. This is like the meat and potatoes of this section. This is like the biggest thing we're going to learn in chapter 3. And what it says is the following. If you consider a polynomial with integer coefficients, it's pretty key. F of x equals this. I know it's a lot to look at, but it just means the highest power is n, and this labeling of a sub n minus 1 are just labeling so we don't run out of letters. It's a way to count the coefficients, actually. So this just means the coefficient of x to the n, coefficient of x to the n minus 1, coefficient of x squared, coefficient of x to the 1, and then the constant term, of course, is the coefficient of x to the 0, if you think about it. So it's just a way to count and label the coefficients of a polynomial. Then we go on to say that any rational zero, so I want to underline integer and rational, I'll talk about that in a second. Rational zero of f of x must be of the form plus or minus a factor of a sub 0, which notice is the constant term, okay, over a factor of a sub n, which is the leading coefficient. Remember, I used LC as our acronym for that. Okay. Now, if you don't remember, integer is a positive whole number or a negative whole number. So these numbers in front of our powers of x's could be positive or negative, but only whole numbers. So 3, 2, 1, no 1/2s, no radical 2s, something like that. So positive 1, positive 2, positive 3, and so on, or negative those. Okay, so like this is a good example of that. The numbers in front, 6, negative 11, and negative 10 are all integers. A rational number is a fraction of integers. So 3 over 5, 6 over 7, 3 is 3 over 1. And I say of integers, so they could be negative. Notice negative over negative is positive, so you get a positive fraction, but technically you could divide positive by negative and so on. The only real exception when it comes to rational numbers is that the denominator not be 0. The numerator can, but the denominator can't. So I'll actually explain why this is true, but first I want to show you an example of it. And in this example, I'm going to explain why it's true. The first thing we need to do is we actually need to figure out what these rational zeros look like. So here's what I'm going to say. I'm going to say RZT for rational zero test will give us the following. We want to look at factors of negative 10 and divide them by factors of 6. Now in reality, we don't care about the sign. Why? Because this plus or minus will handle that for us. So right now, let's just focus on 10 and 6. what are factors of 10? And then what are factors of 6? And then plus or minus those. So here's what we're going to get as our list, and let me write them in braces. So factors of 10 are 1, 2, 3, so I'll write them up. So I got plus or minus, I got 1, 2, I said 3, but 3 is not a factor of 10. Factor, again, is just a number that goes into that number. 1 goes into 10, 10 goes into 10, of course, so 1 in that number itself will always go into the number. 2 and 5 also go into 10, so 2 and then 5. Now, what are factors of 6? So let me write this in red. Factors of 10 were 1, 2, 5, and 10. Factors of 6 are 1, 2, 3, and 6 itself. So there's a lot to do here. Now I need to divide each of these by those. Notice dividing by 1 doesn't do anything, it just gives you those numbers themselves. So this list actually goes on, so I'm going to put a comma and continue below. So now I have plus or minus 1, 2, and 5 again. Over now the next factor, which is 2. Something funny happens though. Here's what happens. 2 over 2 is just 1, which is already accounted for right here. 1 over 1 is just 1. 5 over 2 is something new, but 10 over 2 is 5, which is already accounted for. So once you reduce these things, you find out your list isn't so big after all. We still have to divide by 3 and 6 though, and I think I'm out of space, so I'm going to erase and then show it in the next screen, so let's see that right now. Here's where we left off, and what I'm going to do is I'm going to reduce them and not write them as fractions if possible. So here the first 4, notice, were 1, 2, 5, and 10. Instead of writing them as over 1, I'm just going to write them as the integers only. So now maybe a better way of seeing this is we're dividing every number on top by 1, then by 2, then by 3, then by 6. So this is me dividing them by 1, just writing them. Dividing them by 2, 1 over 2, 2 over 2 is 1, so don't write it. 5 over 2 is new. 10 over 2 is 5. We already have that, so don't write it. So let's continue. And notice when you divide 1, 2, 5, and 10 by 3, there's no reduction. So those will all be new. So we get 1 over 3, plus or minus 2 over 3, plus or minus 5 over 3, and finally plus or minus 10 over 3. No. Going to be a lot to check. What else? Oh, so now dividing by 6. So we get 1 over 6, that's new. And I would say 2 over 6, but 2 over 6 is 1 over 3, which we already have. 5 over 6 is new. And I think that's it, because, of course, 10 over 6 reduces to 5 over 3, which is already accounted for. So we have this huge list of possible rational zeros. So one of these, or maybe more, in fact, at most 2, because the degree is 2, and by FTA, there are 2 real solutions to this equation being equal to 0. So let's move on then. What do we want to do? Oh, well, I guess we want to actually plug these in and see which ones work. I'm going to use synthetic division because if you were to plug it in, you could do that, but it's going to take a long time. Synthetic division will also take a long time, but I'm going to be a little wise about my choices here. So I'm going to think a little bit as I move along, but let's see if we can figure it out together. So using synthetic division, we're checking to see if the result is 0 when you plug it in. So that means the remainder will be 0 because that's what we had from the remainder theorem. That the remainder is what you get when you plug it in. Okay. Now I'm fairly certain none of these first 4 will work, and I'll talk about a little bit later how I know that. But for right now, I'm just going to try to go with the fractions. So let's do 1/2 first. So bringing 6 down for free. Multiply by 1/2, we get 3. Add these, we get negative 8. And then times 1/2 is negative 4. Doesn't quite work. So 1/2 didn't work. So what we can do is we can cross out the plus part of 1/2 because we checked positive 1/2 only. Then checking negative 1/2. So let me erase the work here. So far, this is what we have and what we want. Multiplying by negative 1/2 will give us negative 3. Adding down will give us negative 4. and then multiplying this by negative 1/2 will give you positive 7. They also don't add to 0. So positive 1/2 and negative 1/2 did not work. So now let's move on to the next one and try positive 5/2. And let's see, so 6 times 5 is 30, over 2 is 15. If you add these, what do you get? 4. This is looking good, because 5 times 4 is 20, over 2 is 10, and boom. They cancel out. So positive 5/2 actually worked. Great. This actually tells me something. Since 5/2 is a 0, think of it like this. If one of the answers was x equals 5/2, remember how we would normally do this? We would factor and then set each factor to 0. So what this would imply is that one of the factors is 2x minus 5. This is the only way you can get 5/2 if your coefficients of your linear factor are integers. You would change the sign to positive 5 and divide by 2. Okay? Great. So that means the other factor has to be what? Well, now we can just kind of, actually 2 ways of doing it, but from here we can actually fill in the rest. 2x times 3x will give you 6x squared. Negative 5 times positive 2 will give you negative 10. So that's what it has to be. It has to factor like this. Meaning the other factor, or the other 0, setting this equal to 0, so change the sign of this number and divide by 3, would be negative 2/3, which would be this one. I'm going to circle the negative part of 2/3. And we can actually check by doing the following, believe it or not. We can continue with synthetic division with what we already have, excluding this 0 part. So if we continue with synthetic division and we do negative 2/3, bringing this down and hoping to get a 0 here, 6 times negative 2/3, well, 6/3 is 2, and 2 times negative 2 is negative 4. Or you could similarly multiply by 2 and then divide by 3, you get 12/3, which is 4. So it works, they cancel out. So these are the zeros, and these are the factors that correspond to these zeros. Now, why does this help us understand the rational zeros test? Or at least, how does it help us understand the rational zeros test? Well, notice, if you factor a polynomial, or maybe a better way to think of it, if you FOIL this out to get back your polynomial, what must be true about your last numbers here? These two, let's say. They would have to multiply to this last one. It's not obvious when you have a bunch of factors, but it's still true actually. Because for your last constant term, it's going to just be all of those constants multiplied together. Meaning, all of these numbers, let me underline them in red, will be factors of the last one. Similarly, how do we check that these two have to be 2x and 3x? Well, they have to be factors of this. So the first ones have to be factors of the first one. The last ones in each factor have to be factors of the last one in the original polynomial. Meaning, when you set each of them equal to 0 and solve, it'll be either plus or minus depending on the sign. That's why we had the plus or minus in the rational zeros test set up. Of one of the factors of the last one, notice 5 and negative 2 here, divided by factors of the front one. Notice 2 and 3 here. Okay. So that's all I want to say about this example, and I kind of use it to explain rational zeros test. There's a little more to the explanation of it, but to be quite honest, I think that's convincing enough. We're going to do a few more examples and go a little further with it, so let's see that right now. All right, so in this question, we're asked to solve this equation here. Notice it's a polynomial equation of degree 4, and what we're going to do is we're going to try to factor this, and we're going to attempt to use the rational zeros test to factor. And in fact, you know what? The rational zeros test will just give us a 0, so it's not even necessary to factor this. But I'm still going to show because factoring will come into play in a little bit. We'll see why shortly. But the rational zeros test says that each possible rational zeros of the form plus or minus factors of 6, which are 1, 2, 3, and 6, over factors of, the leading coefficient is just 1, so it's just 1. And notice dividing each of these by 1 will just give you themselves. So the list we have to work with are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Now, there are actually 8 numbers here, because there's 4, but then you have plus or minus for each, so it's 2 times 4 options. So there's a lot to check, and we're going to check again by synthetic division, and let's see. So the coefficients here are going to be 1, negative 1, 1, negative 3, negative 6. Oh, it's a lot to check, I think. After a while, you'll start to get the hang of what will work and what doesn't really work. From the previous example, I didn't say specifically how I knew to stay away from the integers and how I just went straight for the fractions. That's just because I had some insight on how it factored, and I knew that it wouldn't be 6x and x. If it was 6x and x, then the factor that corresponded to x would have only an integer solution. It's a little bit of a deep thought, but in any event, here let's just start straightforward. So let's plug in 1. Notice the first number here is always brought down for free. Multiply by 1, we just get 1. In fact, since we're multiplying by 1, that's our box number, we're just going to bring this number up there. So this is 0, multiply by 1, bring it up, add, multiply by 1, bring it up, negative 2, bring it up, that's negative 8. So that doesn't work. So positive 1 didn't work, now we can try negative 1. All right, so to try negative 1, let me erase a few things here. Okay, good. 1 times negative 1, adding these. When you multiply negative 2 by negative 1, it changes the sign. When you add these, you get 3. Times negative 1 is negative 3. Perfect. These will combine to negative 6. Adding or multiplying to negative 1 will change the sign to positive 6, and they indeed add to 0. Great. Now at this point, you could try to convert back into a polynomial and attempt to factor. If you did in this case, it actually factors quite nicely by grouping, but I'm going to continue. So to continue, remember, negative 1 is a solution. We don't know its multiplicity, so technically it could still work. So we already know that negative 1 worked once. We could check if it works again by trying it once more. So again, we're ignoring the 0 part here. All right, so if we try negative 1 again, we get what? We get negative 1, negative 3, positive 3, positive 6. Negative 6, they don't quite add to 0. They would combine to negative 12, so this doesn't work. Okay, so negative 1 is only a solution once. What about 2? So we can try positive 2. Multiplying by 2 gives us 0. When you add these, you get 3. There we go. 3 times 2 is 6, and there it is. Okay, so now what? Well, now we can try the other ones. Again, you can try 2 again, so we know negative 1 and positive 2 work. But I'm going to tell you right now that nothing else will work, actually. None of these other numbers here will work. As it turns out, negative 1 and 2 with multiplicity 1 each are the only rational zeros or solutions to this equation. How do I know that? Well, I know that because in my head already, I'm looking at this and I'm converting it into a polynomial. And as a polynomial, this is x squared plus 3. And x squared plus 3 can't be factored. In fact, you can actually solve for this being 0. If this was equal to 0, notice you get x squared is equal to negative 3. So when you square root, you get x is equal to plus or minus the square root of negative 3, which is not real. In fact, remember how we did this? When you have a negative instead of the square root, an I comes out. So we get x is equal to plus or minus I times radical 3. All right, so in total, what have we found out? We found out that our solutions are x equals negative 1, positive 2, positive I radical 3, and negative I radical 3. Perfect. So these are the 4 solutions to this equation, and it checks out with FTA because the degree is 4, so there should be exactly 4 solutions if you consider non-real numbers and multiplicity. Of course, here there was no repeat, but we still had non-real solutions. So that was nice. and it was using the rational zeros test. So we'll see a few more examples, and then we can end it for 3.4. Right, so this is actually going to be the last example we're going to do. Sorry for the color change, by the way. I don't want the video to be too long, so I think this is okay for the last example. Notice the numbers are kind of large, so it's going to get a little crazy, but let's see, we can handle it, I think. We first want to apply again the rational zeros test, which basically says we need to look at factors of the constant term divided by factors of the leading coefficient with pluses or minuses. So we're going to write out the set of plus or minus. Factors of 15 are 1, 3, 5, and 15. Remember, it's always 1 in itself, and then anything that can go into 15, in this case 3 and 5. And then 16, a lot goes into 16. It's 1, 2, 4, 8, and then 16 itself are all factors of 16. And let's write them out. And yikes, here it is. It's a lot to look at. There are a lot of things, nothing actually reduced. I notice 1, 3, 5, and 15 are not divisible by 1, 2, 4, 8, or 16. Well, I guess by 1 they are, but by 2, 4, 8, or 16 they're not. So there's a lot to check here, and I'm going to check all of them by synthetic division. Well, not exactly. I'm going to show you a way that you can actually figure this out with your calculator, which one works, because there's a lot. So there's this kind of nice thing we can do. If you have a TI-83, you can definitely do this. Okay, so once pressing y equals, it'll take you to this screen. You type in your polynomial, and then press second window, which is table setup. Make sure independent is set to ask, not auto. That'll ask you what x is. So here, once you press second graph, which is table, it'll let you plug in your own x values like this. Here I plugged in a few. And notice what we're aiming for is y to be 0. So far, we have none. Here it says 0.5, but notice at the very bottom I type in 1/2, and then it converts it to decimal. And here finally we see negative 0.75, which is negative 3/4, is our first 0. Right, so in using the calculator method to help refine our search here to make it speed up things a little bit, we found that only negative 3/4 actually works. So this appears to be the only rational 0. Let's see what happens. So we're going to still play the game of synthetic division to check. We should get a 0 as a remainder. Let's see what happens. So if our box number is negative 3/4, and we have coefficients 16, negative 20, negative 4, and 15, remember what happens. We bring this down, multiply by negative 3/4. 16/4 is 4, times negative 3 is negative 12. If you add these, you get negative 32. Negative 32/4 is negative 8, and negative 8 times negative 3 is positive 24. Adding these, we get 20. Perfect. 20/4 is 5, and 5 times negative 3 is indeed negative 15. They combine to 0. But now, what about this? What about this polynomial? What does this correspond to? Well, if none of these other ones worked, that tells me there are no other rational zeros, meaning that the zeros of the remaining polynomial, the quotient polynomial basically, will actually be irrational. And we can check that by using quadratic formula. So let me erase this, convert this to a polynomial, and apply quadratic formula, and we'll see what we get. Right, here it is. So this is the polynomial, 16x squared minus 32x plus 20. These are the a, b, and c values, 16, negative 32, and positive 20. Also, I kind of misspoke earlier when I said they'll be irrational. They may be non-real. I'm not quite sure yet. I haven't tried it yet. Well, one thing I do want to say actually is we can actually make a little less work here because the numbers are kind of large still. Notice we can divide each of them by 4. So let's actually do that. That'll actually reduce things a little bit. So if you divide everything by 4, what you can do in an equation, because it's a non-zero number, we actually get something else. We get 4, 8, and 5 instead. 16/4 is 4, 32/4 is 8, and 20/4 is 5. So actually, we have smaller numbers to work with. 0/4 is 0, of course. So now A is 4, B is negative 8, and C is 5. It's a lot more easy to work with than the other numbers, 16, 32, and 20. So let's plug these in. Remember, quadratic formula is negative b. Since b is negative 8, that's going to be positive 8, plus or minus the square root of, let's see, it's going to be b squared, which is 64, minus 4 times a times c. This is the moment of truth because this will tell us if we're going to get a negative on the inside or not, and I think we will. Notice 4 times 4 is 16, and 16 times 5 is 80. And yeah, we indeed get a negative, so it is a non-real number. Well, two non-real numbers because of the plus or minus. And of course, it's all over 2a. So 64 minus 80 is negative 16. The square root of 16 is 4. 4 times 2 on the bottom is 8. The square root of 16 is 4, but since negative 16, the square root of negative 16 is 4i. So this is going to be 8 plus or minus 4i all over 8. And remember what we do here, we split it up as 8 over 8 plus 4 over 8i, plus or minus 4 over 8i. So that actually reduces to the following. X is equal to 1 plus or minus 1/2 i. And believe it or not, these will actually work with synthetic division. I don't want to do it because it's a little bit involved in multiplying a complex number by another complex number. It's FOILing, so it's not too bad. But you can try it yourself to check to see this indeed works. But it does, so that's all I'm going to say here. Now, here are my two zeros that are non-real. Here was my zero that was real, it was rational. And I'm going to write out the list of zeros, and then from there I'm going to factor. Here it is, here are the zeros, the 3 zeros. Notice our degree is 3, so it checks with the fundamental theorem of algebra. Negative 3/4, so 1 plus 1/2 i and 1 minus 1/2 i. And now finally, for the factorization part. So to factor this, here's what we're going to do. We're going to write f of x as the leading coefficient, which is 16, times x minus each factor. So x minus negative 3/4 times x minus 1 plus 1/2 i times x minus 1 minus 1/2 i. Kind of ran out of room there, and I'm missing a parenthesis, but that's okay. Just imagine that's nicer looking than it actually is, but that's okay. Hope we can see, hope that comes out okay. So right, changing some of the signs here. So the double negative there will be plus 3 over 4. This is going to be distributing the negative here. Will be x minus 1 minus 1/2 i. This is going to be x minus 1 plus 1/2 i. And there's something I kind of want to do with the 16. I want to split 16 up to get rid of the fractions. And you don't have to. So right now, this is my answer, is pretty clean enough. But just for completion, I'm going to do this. I'm going to notice that 16 is 4 times 2 times 2. So I'm going to distribute it into each of these individually as such. So 4 will distribute into this. So it'll be 4x plus 3. 2 will distribute into this one. So it'll be 2x minus 2 minus I. And 2 into this one, that's going to be 2x minus 2 plus I. Now that sounds a little bizarre, but it works out actually. So remember, 16 is 4 times 4. So one of the 4's is distributed into this. We get 4x, and here the 4's cancel, you should get 3. The other 4 is split into two 2's. One 2 goes into this one to cancel that 1/2, and the other 2 goes into that one to cancel that 1/2. So in my opinion, this looks a little nicer of a factorization into linear factors. But, you know, it's really preference, I guess. But yeah, that was using the linear factorization theorem. And that is it. That ends this fun section of 3.4, which was, again, zeros of polynomials. That actually ends chapter 3. I know this was kind of a long video, but thanks for watching all of the nice examples here. There are a few homework problems in here, so it's nice to go through those. And yeah, I'll see you in the next videos. Thanks for watching.